Welcome, this is Professor Ridge and today's lesson 5.2 Power Functions and Polynomial Functions. Our first objective, identify power functions. Identifying power functions. Before we can understand the bird problem, it'll be helpful to understand a different type of function. A power function is a function with a single term that is the product of a real number, a coefficient, and a variable raised to a fixed number. So you can see in the definition here, a power function can be represented in the form of f of x equals k times x to some power. K and p are real numbers, and k is known as the coefficient. So you're going to have some number times x to some power, some real number power. Okay, and it says example 1 here, identify power functions. So which of the following are power functions? F of x equals 1, f of x equals x, f of x equals x squared, f of x equals x cubed, f of x equals 1 over x, f of x equals 1 over x squared, f of x equals square root of x, and f of x equals cube root of x. And here's the name of those functions. We should be familiar with all of these. These are also our basic toolkit functions that we should know how to graph real quickly. And again, so which of these are power functions? And it turns out they're trying to throw a little curveball at you here. They're actually all power functions. And the way you can write it, so for the first one, the constant function, f of x is 1. Even though you don't see it, you can always put x to the 0. So we have a constant or variable x to a 0 power. X to the 0 is just 1. So technically this could be considered a power function, right? Although I mean, it's not going to behave the way that we're going to talk about most power functions, but technically it is a power function. And then this one, same thing. You can, anytime you have just a variable, the coefficient's 1 if you don't see it. And then the exponent is 1. Okay, so then we have 1x squared, 1x cubed. Now this one, the reciprocal one, the trick on that one is you have to know your exponent rules. If you have x to a negative exponent, that's the same thing as 1 over x to the n. So we can rewrite this as 1 over x is the same thing as x to the negative 1 power. So we have our coefficients 1 and our exponents negative 1. And then for the reciprocal squared function, same thing. We can rewrite it as 1 times x to the negative 2. Okay, and then for square roots, you have to remember our rational exponent rule that x to the 1 over n is equal to the nth root of x. So for the square root function, you can rewrite it as a power function as 1 times x to the 1/2. And then our cube root function, same idea, using that same rule, we can write it as 1 times x to the 1/3. Okay, so they were all power functions. All right, our next learning objective, identify end behavior of power functions. Identifying end behavior of power functions. So figure 2 shows the graphs of f of x equals x squared, g of x equals x to the 4th, h of x equals x6, which are all power functions with even positive integer powers. And notice that these graphs have similar shapes, very much like the quadratic function in the toolkit. So however the power increases, the functions flatten out somewhat near the origin and become steeper away from the origin. So look at this behavior here. So for the blue one, or for our basic toolkit function, the x squared is our nice U parabola shape, right? Now look at the x to the fourth. You see, basically, if you look at this first unit here, so we have the x squared does that. Well, it should hit the bottom there. But x to the fourth kind of flattens out a little bit and then gets steeper. And then x to the sixth would be even more pronounced. Okay? So that's the idea. So the higher the power, if it's even, it's going to exhibit this. In fact, let me show you on Desmos. Okay, so here's Desmos. So I have y equals x squared, x to the fourth, x6, x8, your parabola. So I'm going to turn on one at a time, and you can see. And you can, let's zoom in on this between 0 and 1. Okay, so you can see that x to the fourth, it flattens out, and then it's steeper. So that kind of, that U shape, it's actually a better U shape now. Okay, now let's look at x to the sixth. Well, let's compare it. Right, so you can see that even flattens out more. So here's the original one, the red, x6, x4, okay, and the purple, it's even more pronounced, that flattening. Now let's go to x to the eighth, and you can see it flattens out even more. So it's gonna, if I were to zoom in, it's hard to tell, but it's not exactly 0. It rounds it to 0. It's not 0 anywhere until it hits 0, 0, 0. But if we did 0.5 to the 8th power, it's going to be 0.0036, and so on. Okay, so it flattens out. And then if we did x10, even more so, x12, even more so. You can see that. Okay, so it has that same basic shape, but as you get, if it's an even power, and notice that the leading coefficient is positive, so we're going to talk about this later. If I make the leading coefficient -1 from our transformations, we know that's going to flip it over. It's going to flip it over the x-axis, right? So if we had -1 in front of there, or negative, okay? So if it's positive, even power, both ends are going up, right? Positive, even powers, both ends are going up, because we're talking about the end behavior. Okay, both ends are going up, so on. Okay, so again, to describe the behavior as the numbers become larger and larger, we use the idea of infinity. We use the symbol infinity for positive infinity and negative infinity for negative infinity. So the minus sign and this like sideways 8, that's infinity. When we say that x approaches infinity, which can be symbolically written as okay, so here's how you write it, as x, and then the arrow we say approaches infinity, right? So that's how we write in symbols. So if you think about it for a second, so as x is going to infinity, that's saying it's going to the right. So I call this the right end. Right end, we are describing a behavior. We are saying that x is increasing without bound. So that's basically, I call that the right end. And with the positive even power functions, as the input increases or decreases without bound, so we're talking about what's the right end doing, what's the left end doing. So if the input increases, that's the right side. As it decreases, that's the left side. The output values become very large positive numbers. So the way we'd write it in symbols, well, let me finish reading this for you. Equivalently, we can describe this behavior by saying that x approaches positive or negative infinity, so either the right end or left end. The f of x values increase without bound. So in symbolic forms, we can write, and typically you're going to say, so for the right end, we're saying as x approaches positive infinity, then the y values are going to positive infinity. So as I go to the right, the y values are increasing without bound, right? So the right end is going up. That's the way you interpret that. As x approaches negative infinity, that's the left end, the y values are going up, going to positive infinity, or increasing without bound, however you want to say that. So I say that the left end is going up, right? So that's kind of the way I describe it. Okay, so now let's look at the odd ones. So figure 3 shows the graph of f of x equals x cubed, g of x is x to the 5th, h of x is x to the 7th, which are all power functions with odd whole number powers. Notice that these graphs look similar to the cubic function in the toolkit, so the x cubed one. And again, as power increases, the graphs flatten out near the origin and become steeper away from the origin. So similar, it's the similar idea that we did with the x squared, x4, x6, and so on, right? It flattens out as you are close to the origin, and then it's steeper. So the higher that number, the steeper this curve is going to be. So again, let me show you that on Desmos just so you can see it. Okay, so here's x cubed. So remember, if you're going to do this by hand, here, let me zoom out. For the x cubed, it's 0, 0, 1, 1, and then 2 cubed is 8. And then you can draw this kind of, I don't know what you call that. It's a cube curve, kind of a S kind of sloping curve. So 0, 0, 1, 1, 2, 8. Then negative 1 cubed is negative 1. And negative 2 cubed is negative 8. You can't see that. Okay, negative 2 cubed is negative 8. If I can hit it, there we go. Okay, so that's our basic toolkit function at y equals x cubed. And if I zoom in, if I do x to the 5th, it's going to have a similar shape, except it, just like we did with the x squared, it kind of flattens out right here between 0 and 1, and then it's steeper as we go further away. And then on the left side, since it's cubed, that's going to negative infinity. All right? And then you can see if I do x 7th, it's even more pronounced, flattening out. All right? So there's x to the 5th. X to the 7th is the purple. Then x to the 11th would be even more pronounced. Okay? See that? And if I zoom in again, so then it crosses. Oh, I should have had a different color. Let's see here. All right, so you can see as it crosses, it's steeper, so it's going up to infinite. It's increasing at a faster rate. All right, so let's get back to the book. Okay, these examples illustrate that the functions of the form f of x equals x to the n reveal symmetry of one kind or another. First, in figure 2, we see that functions f of x equals x to the n if n is even are symmetric about the y-axis. So let's go back and look at that. We didn't talk about that before. But if you did a vertical line through the, we have, for a parabola, we know it has the axis symmetry through the vertex. So these are symmetric about the y-axis. If I fold the graph, if it was on paper, and I fold the graph on the y-axis, the left side and the right side would match. Okay, so that's symmetric about the y-axis. Now for odd ones, we see that odd functions, n is odd, it's symmetric about the origin. And if you'll recall, symmetric about the origin is if I were to put if it's on paper, put my finger at the origin and spin this 180 degrees, it would look the same, right? If I didn't have anything labeled numbers, but just put my finger at the origin, spin it 180 degrees, it would look the same as it started. Okay, so that's symmetric about the origin. And again, if you remember, the technique is, for instance, for y, well, for all of them, they all go through 1, 1. So if it's symmetric about the origin, the symmetric point about the origin, you switch both signs. Okay, so we switch both signs. So that if this is 1, 1, then I know -1, -1's on it. And then like I showed you before, if I had 2, 8, then it'd be -2, -8. All right? So for these odd power functions, as x approaches -infinity, f of x decreases without bound. As x approaches infinity, f of x increases with bounds. So in symbolic forms, as x approaches -infinity. So remember, this is, we're saying the left side goes up. Oh no, sorry, it's going to -infinity. So this is the left side as x goes that way, the y values are going down. Okay, goes down. Let me try that again. Goes down. So that's the way I interpret this. So the left side's going down. And then as x goes to positive infinity is going to the right. So this is the right side. And then f of x is going up. Okay? Up. So the right side goes up. That's the way I interpret this notation. So the behavior of the graph of a function as the input values get very small, so that's the x goes to -infinity, and get very large, x goes to infinity. So again, I should change the side to end. Let me try that again here. So let's call that the right end. So this would be the left end, because it's the end behavior. So right side, right end, left end. So this is the left end, goes down, and this one's the right end goes up. Okay, so this is called end behavior. That's the key. All right, so the behavior of the graph as the input values get very small, so that's x going to -infinity, or the way I say it, it's the left end, and get very large, so as x goes to infinity, that's the right end, is referred to as the end behavior of the function. So we can use words or symbols to describe end behavior. Okay, so if we wanted to talk about the end behavior of a graph, f of x equals k times x to a power. So this is our basic power function. So if k is positive, I just think of x squared and x cubed to so I don't really memorize this chart. I just think of x squared and x cubed. And let's see, so if k is positive, that would be a parabola opening up. So the ends, both ends are going to go up. And then if I think of x cubed, I think of this one. So the left end goes down, the right end goes up. And again, in notation, I don't know why they should have as x. Okay, so as x approaches -infinity, so I would actually write as in front of for this notation. But that's fine. So as x approaches -infinity, so that again, that would be the left side or the left end. F of x approaches -infinity. So again, the words are as x decreases without bound, or I like to say the left end, and then f of x, that's the y values, decrease, sorry, that's going to -infinity. So again, I would say the left end is going down. Left end is going down. Right end is going up. So the right end, so the left end's going down, right end's going up. That's what these two notations are. Now, if you times this by a -1, it makes the function flip upside down. So now both ends are going down if it's an even power. If it's odd power, then we flip. The left end's going to go up, left end goes up, and then the right end goes down. Okay? So either you memorize that chart or you do like I do, just think of x squared and x cubed. And if you kind of forget, then you can, just make it a little XY chart and pick like -10 and +10 and see what those Y values are, and that'll help you know, is that going, so -10 is over here, is that going up or is it going down? Just figure out what that Y coordinate is. And then the same thing on the right side, that'd be the +10. Is that going up or is that going down? Okay? And just put it into the power function part. Okay, so given a power function f of x equals kx to the n, where n is a positive integer, identify the n behavior. So determine whether the power is even or odd, determine whether the constant is positive or negative, and then use figure 4 to identify the n behavior. And again, like I said, I don't memorize this chart. I just think of x squared and x cubed, and then I just kind of use that. X squared would be for the evens, x cubed for the odds. Okay, so this is x8, so that is an even power. So that's our first step. So is it even or odd? So for me, when I think x squared, I'm going to think, even power, I'm going to think x squared, which I know is a parabola opening up. So I just got to check, is the constant in front, is this positive or negative? So it's a positive one. So the constant is positive. So that's just going to be my basic like parabola, but again, it's x to the 8th, so it's actually going to flatten out and be steeper. Okay, but all we're concerned about right now are the ends. So what are the ends doing? So the left end is going up and the right end is going up. So I think the way the book wants you to do it is with the notation, or you can write it in the words. So as x goes to negative infinity, so that's our left end, the y values, f of x, goes to positive infinity. And then as x goes to positive infinity, so this is the right end, the y values are also going up. So f of x goes to infinity. So again, technically this is as x approaches infinity, is as x increases without bound, y increases without bound. I just simplify it. The right end is going up, and then on this one, left end is going up, or both ends are going up. Okay, let's look at example 3. Identify the end behavior of the power function. Describe the end behavior of the graph f of x equals negative x to the 9. So again, we have two things we need to know. Is it the power even or odd, and is the constant positive or negative? So our first step, so 9, the power is 9, so that's an odd power. And it's -1, so the constant's negative. Constant is negative. So again, I just think x cubed. I know my x cubed, my toolkit function does that. And so if it's negative, it flips it around. It's going to do that. And since it's 9, again, it's going to kind of flatten out as we get to the origin and be more pronounced. Right? It's going to be flat and not more pronounced. It's going to be steeper. Okay, so this would be, so the left end is as x goes to negative infinity. So this is positive, this is negative. Okay, so what's the left end doing? It's going up. So we say f of x goes to infinity. Now look at what's the right end doing. So as x goes to positive infinity, or just infinity, that's a sideways 8 is the way I think of it when I write it. the y values are going down, so that'd be negative infinity. All right, and as simple as that. So you have two options. You can kind of think of it the way I do. I just think x squared for my evens, and I use that for all the evens. And I think of x cubed for odds, and I think of that for all my odds. Or you can memorize this chart. Okay, so it's up to you. And then a third way, if you want, you can just put in like negative 10 and 10 into that and just see what the end's doing. Okay, our next learning objective, identify polynomial functions. Polynomial functions. Let n be a non-negative integer. A polynomial function is a function that can be written in the form f of x equals a sub n times x to the n plus dot 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 plus a sub 2 x squared plus a sub 1 x, and then that would be to the first, plus a sub 0, and there's no x, but technically it's x to the 0. And we call this last term the constant term. Okay, this is called the general form of a polynomial function. And again, like I was saying earlier when we're doing quadratic functions, some books call this standard form polynomial function. So take it for what you will. Each a sub I is a coefficient and can be any real number. So those are what we call the real number coefficients, the a, and the subscript just matches what power you're on. So if this is degree 5, we say a sub 5 x to the 5th, right? So we can match the coefficient with the what we call degree. So that power, we call it degree. You'll hear me say that a lot. Okay, but a sub n cannot be 0. Okay, so this first one can't be 0, but any other term can be 0. Each expression a sub I x I is a term of a polynomial. So the terms are separated by these plus signs. And technically, right, if you think of adding a negative number is the same thing as subtracting. So it could be, they're separated by plus or minus signs. But technically, from the definition, the terms are separated by these plus signs. Okay? Example 4, identify polynomial functions. Which of the following are polynomial functions? Okay, so we want it to be, it says, now here's a key on a lot of these definitions. It says can be written, not it is written this way. So even though this doesn't look like that form, I can simplify this and say, okay, well, that's equal to, I can multiply, right, I'm going to rearrange this. So 2 times 3 times x cubed times x, since that's all multiply, and it's commutative and associative, which means you can rearrange the order and combine it. So 2 times 3 is 6, x cubed times x is x to the 4th. And see, now this is in this form. We got a constant, so a sub 4 would be 6, x to the 4th, and then these are all 0 except the constant term is 4. So that one's a polynomial. Okay, this one, same thing, right? We can distribute the negative, and we get negative x cubed minus, a minus becomes plus 4x. And again, we got negative 1 for our a sub 3, because this is 3, x to the 3, plus, and we go what we call descending order. So that's x cubed, x squared is 0, or sometimes, and we can refer to that as a missing term. The x term is 4x, so that would be this one. A sub 1 would be 4, x to the 1, and then the constant term 0. So that one's a polynomial as well. Okay, now this one, no, you can't. There's no way you can simplify this and make it look like the polynomial without changing the value of this, right? So that's key. We can't change the value. You can say, well, you can use square root as power 1/2, but remember, n has to be a non-negative integer. So if the integer is a negative integer or a fraction, meaning not an integer, then it's not a polynomial. So no, not a polynomial. I'm just going to write poly. Okay, so it's not a polynomial. Okay, and on to our last learning objective, identify the degree and the leading coefficient of polynomial functions. Identifying the degree and the leading coefficient of a polynomial function. Because of the form of a polynomial function, we can see an infinite variety in the number of terms and power of the variable. Although the order of the terms in polynomial function is not important for performing operations, we typically arrange the terms in descending order. That's what I was talking about earlier, or in general form. So in general form, we want it descending order. Okay, the degree of the polynomial is the highest power of the variable that occurs in the polynomial. It is the power of the first variable if the function is in general form. Okay, so a polynomial doesn't have to be in descending order, but the degree of the polynomial will be the highest degree term, and if you put it in general form, which is put it in descending order, then it's going to be the leading term. So the leading term is the term containing the highest power of the variable, or the term with the highest degree. So again, that comes from if we put it in, so it doesn't have to be in descending order, but if we put it in general form, you write the highest degree term first, and then since it's in that form, it'd be what we call the leading term. Okay, but the leading term is always the term with the highest degree power. Highest power of the variable. And we call that the degree. Sorry. Okay? So the leading coefficient is the coefficient of the leading term. So if it's in descending order, the first one will be the leading term. If it's not in descending order, it's still the highest degree term. Okay? The degree is the power. So in this case, this is the nth degree polynomial. The leading term is the whole term, a sub n x to the n. And the leading coefficient is just the coefficient of the leading term. So it'll be a sub n. Okay, so let's look at example 5. Identify the degree and the leading coefficient of polynomial. Okay, so the degree, the leading term, leading coefficient. So you're going to find the highest power of x to determine the degree. So remember, it doesn't have to be in the general form or in descending order. Okay, so do you see how this, remember I said that terms are separated by plus signs, but technically, but if you wrote plus a negative 4x cubed, right, this is the term, but then it's more simple to write it. Plus a negative means the same thing as minus 4. Okay, so that can be confusing. So you got to take that negative with the 4, and the term is negative 4x cubed. And that's the highest power. It's degree 3. This one's degree 2. And this is x. This is 3x to the 0. So that's degree 0. So degree 0, degree 2, degree 3. So the highest degree is 3. So that's going to be the degree of the polynomial. Is equal to 3. The leading term is the whole term. Is negative. You got to write the negative, 4x cubed. And the leading coefficient, I'm just going to write coef like that. Leading coefficient is just the number part, negative 4. Okay? And then for g, the degree is, so we got 5, 3, and 1. So 5's the highest one. So the degree is 5. The leading term is the whole term, 5t to the 5th. And then the leading coefficient is 5. And then for h, let's see, we got 1, 3, and 0. So the degree is 3. The leading term is what? So again, be careful. You got to take this negative with it. So basically these are the 3 terms. Okay, so 6p negative p cubed negative 2. So this is the highest degree term. So that will be the leading term. And again, it comes from when you're thinking of it if it's in descending order. So if you put it in descending order, you're going to lead with this term. So the leading term is negative p to the 3rd. Okay? And then the leading coefficient is the number part. And remember, that could be thought of as negative 1 times. So negative 1. Identifying end behavior of polynomial functions. So knowing the degree of the polynomial function is useful in helping us predict its end behavior. Okay, so our end behavior, back to what we started with today. To determine its end behavior, look at the leading term. So to figure out what the ends are doing, all we care about is what's the leading term. Because the power of the leading term is the highest, that term will grow significantly faster or decrease significantly faster than other terms as x gets very large or very small. So its behavior will dominate the graph. So that leading term is just going to overpower all the other terms when the numbers get very large or very small. Okay, so for any polynomial, the end behavior of the polynomial will match the end behavior of the power function. See table 3. So basically, if the leading term is an even power, we just have to refer to the power function. An even power, both ends will go up or both ends will go down, depending on if the leading coefficient's positive or negative. So we can extend that. Extend here. Let me go back to this chart. We can extend this chart for any polynomial, not just the power functions. And so we're going to look at just what's the leading term and then apply this chart for just the ends. The middle can do all kinds of crazy things. So they show you a bunch of graphs. Here, hang on. Okay, so again, they show you a bunch of graphs. And you look, if you have f of x is equal to 5x fourth plus 2x to the 3rd minus x minus 4, all we care about, if we want to know what the ends are doing, the only term that we really have to focus on is the leading term. And again, this has to be descending order. So this is degree 4, so that's even, and the leading term is positive, leading coefficient's positive. So we think of, again, the way I do it, I just think of x squared. So the left end's going to go up, the right end's going up, and you can see that that's happening. Now the middle does other things. So as you get close to 0, the middle can do all kinds of crazy things. But as x gets large or small, if you go to positive infinity, the right end's going to go up, and the left, as you go to a negative infinity, the left end's going to go up. Okay? So again, we call this the leading term test. So we can take that end behavior and apply it to any polynomial and just look at the leading term. Okay, that's the key takeaway. Okay, so let's look at the remaining 3 graphs the book presents. So if you look at this one, the leading term is negative 2x to the 6. So you have x to the 6, so again even, so I think of my parabola. If the leading coefficient's positive, it opens up. If it's negative, it opens down. So again, I'm thinking of my parabola it opens down. So what's the left end doing? Going down. What's the right end doing? Going down. Okay? Now if we do cubes, 3x, or this is x to the fifth, 3x to the fifth, and I said cubes because remember, if it's an odd power, I just think of my toolkit function, x cubed, right? And if the leading term's positive, it does this. If it's negative, it flips upside down. So for my x cubed, what are my ends doing? The left end's going down, and see this x to the fifth, it does the same thing. So all the odd ones are going to behave the same way, 3, 5, 7, so on. Okay, so the left end goes down, right end goes up, and you can see the right end goes up. And then this one's a cube again, but it's negative, so it's going to take this basic toolkit function one and flip it upside down. So it's going to do this. So the left end's going to go up, and you can see the left end goes up, and the right end's going down. Now again, I want to iterate these other terms kind of messes up what goes on in the middle. So it's not going to be a straight function like that. We have these humps in the middle, and that's caused by the, let me erase all that scribbly. That's caused by the other terms. But eventually the ends are going to get dominated by the leading terms. So if we want to know what the ends are doing specifically, we just have to look at the first term, the leading term. Okay, let's look at example 6 now. Identify the end behavior and the degree of the polynomial. Describe the end behavior and determine a possible degree of the polynomial function. So again, we're going to look at the ends. So look at this end, that's the left end. Left end goes down. So remember the way we described it. So that would be as x goes, so going to the left on the x-axis, that's going to negative infinity, and going down, that's the y values, so f of x goes to negative infinity. And then this end, this is the right end. Okay, so the right end is as x goes to infinity, f of x, okay, so the right end is going up, so it goes to positive infinity. Okay, so left end, top box, right end, bottom box. Example 7, identifying end behavior and degree of polynomial. Given the function f of x equals negative 3x squared times the quantity x minus 1 times the quantity x plus 4, express the function as a polynomial in general form, determine leading term, degree, and end behavior. Okay, so we need to put this in general form, so we need to multiply it out. So I'm going to distribute the negative 3x squared. So that'd be negative 3x cubed minus a minus becomes plus 3x squared. And then I got to distribute it now with the x plus 4. So then I do the FOIL. So negative 3x to the fourth minus negative 3x cubed times 4 be minus 12x cubed plus 3x cubed, and then the last terms be 12x squared. I can combine my like terms, those middle terms. So negative 3x to the fourth minus 9x cubed plus 12x squared. And now it's in general form, and you can see the leading term is negative 3x to the fourth. The degree is 4, and the leading coefficient, I should add that, leading coefficient, even though they didn't ask for it, I still need to know it, is -3. So if the degree is even, so I'm going to think of my parabola, and the leading coefficient is negative. It's the parabola opens down. So I'm going to extend that just for my left end and my right end. So as x goes to -infinity, that's the left end, f of x goes to -infinity. And as x goes to +infinity, that's the right end. The right end is going down. So f of x goes to -infinity. Identifying local behavior of polynomial functions. So in addition to end behavior of polynomial functions, we are also interested in what happens in the middle of the function. So not just the ends, what's going on in between, right, in the middle. In particular, we are interested in locations where graph behavior changes, or we call them turning points. A turning point is a point at which the function value changes from increasing to decreasing, or the other way around, decreasing to increasing. And if you recall, that's where we have our local maximums and local minimums. So if we're increasing and then we stop and turn around and start decreasing, that's going to give us what we call the turning point, and we also can refer to it as a local maximum. And if we're going from decreasing and we turn around and start increasing, that's going to give us a local minimum. So those are called turning points. And again, we are also interested in intercepts, right? That's always a big deal. Find the x-intercepts, find the y-intercepts. So as with all functions, the y-intercept is the point at which the graph crosses or intersects the vertical axis, which is the y-axis. The point corresponds to the coordinate pair in which the input value is 0, because in a polynomial is a function, only one output value corresponds to each input value. So there can only be one y-intercept. Okay, there will be only one y-intercept. The x-intercept occurs at the input values that correspond to the output values of 0. It is possible to have more than one x-intercept. See figure 9. Let me copy that. All right, so here's figure 9. You can see our turning point. The function's increasing, decreasing, so we got a turning point. And again, that would be considered a local maximum. And then here's another turning point. We're decreasing, and then we increase. So that'd be a local minimum. The graph crosses the x-axis 3 times, so we have 3 x-intercepts. And remember, it's xy, so it's the x-coordinate, comma 0, x-coordinate, comma 0, x-coordinate, comma 0. So this one would be 1, 0. This would be -2, 0. This would be -4, 0, assuming that this is your basic scaling, 1, 2, 3, so on. Okay, and then you have your y-intercept be 0, whatever the y value is there. So 1, 2, 3, 4, 5, 6, 7, 8. So 0, -8. Okay, so again, from this figure you can see there's only one y-intercept and there's 3 x-intercepts. So x-intercepts you can have none, you can have 1, 2, 3. In fact, we'll learn later, you can have up to in whatever the degree of the polynomial. So if this is a 3rd degree polynomial, you can have up to 3 x-intercepts. Example 8, determine the intercepts of a polynomial function. Given the polynomial function f of x equals x minus 2 times x plus 1 times x minus 4, written in factored form for your convenience. So we have the 3 factors. X minus 2 is the first one, x plus 1, and then x minus 4. Determine the y and the x-intercept. So when it's factored, it makes finding the x-intercepts really easy, because we need to find the x-intercepts. Remember, it's some number 0. We're going to plug in 0 for y, or the f of x. So we're going to set this function equal to 0, and then we need to factor it and set each factor equal to 0 using the zero product property. Okay, so if it's factored for you already, then that's the hard part. So now we have it factored equal to 0, and then we're going to set each factor equal to 0 and then solve for those. And we'll get the 3x coordinates for the 3x intercepts. So if you have 3 factors, then you're going to get 3x intercepts. So add 2. So x is 2. Now do the middle one, subtract 1, so x is -1. You can skip the step, just remember the shortcut. You're going to move it, change the sign. So if I move this -4 to the other side, it becomes +4. So my x-intercepts are 2, 0, comma, -1, 0, comma, 4, 0. Okay, and now to do my y-intercept, y-intercepts, it's 0 for x, and then you figure out f of 0. Okay, so we plug in f of 0, or we plug in 0 into f. So f of 0 is 0 minus 2, 0 plus 1, 0 minus 4. So what's -2 times 1 times -4? That looks like 8. So our x-intercept is, or y-intercept, sorry, is 0, 8. Now, let's go to Desmos and I can show you that. Okay, so I typed it in Desmos, and what's nice with Desmos is you can just click on the graph here and it'll show you. Okay, so we got the -1, 0, 2, 0, 4, 0, and I believe that's what our answers were, right? 2, 0, -1, 0, 4, 0. Yeah, just different order, which is fine. And then the y-intercept, let me zoom in over here, is 8, 0. And another nice feature with Desmos, they'll show you those turning points as well. We actually need calculus to figure, well, to figure this out easily, you need calculus, but you can guess and check and kind of hone in on it, but it's numerically, but it's not very easy without calculus. Okay, so those are the turning points. So again, our x-intercepts, which we found by setting the function equal to 0 and then solving it, and then the y-intercept, which we found by plugging in 0 for x and then figuring out what the y was. Okay, and then you can check using Desmos. Let's try example 9. Given the polynomial function f of x equals x to the 4th minus 4x squared minus 45, determine the y and x intercepts. Alright, so the y-intercept's the easy one. Let's start with that one. Remember, it's 0, f of 0. So if I put in 0 for x, 0 to the 4th, minus 4 times 0 squared minus 45, well, all these terms go away and we just get the 45, negative 45. Be careful. So 0, negative 45. Now for our x-intercept, remember it's going to be, we got to figure out what x is when we set it equal to 0. So x fourth minus 4x squared minus 45 equals 0. Now you got to factor this. This behaves like a quadratic equation, so we can factor it using the FOIL method, the reverse FOIL method. Right? Factors of 45 that subtract to 4, but instead of these being x's, they're going to be x squares, because x squared times x squared is x to the 4th. You can do the use, did we cover, I think we covered you doing a use substitution before. You can do that way too, but this is the way I do it. Just it's 3 terms, x fourth, x squared. Factors 45 that subtract to 4. So I run through all my factors of 45. Usually I check the first thing pops in my head before I write anything down. I don't ever write anything down, but I typically, with the calculator, start with 1, go to 2, 3, 4, 5, and then I want it to subtract to 4. So 1 and 45, 2, right? But usually for this, the first thing that would pop in my head would be 5 times 9, which is 45. 9 minus 5 is 4. So that's where I'm going to get. And the bigger one gets, the bigger of the two factors gets that middle sign. And to get a negative 45, these have to be opposites. So hopefully your factoring skills are getting better. If not, you just got to keep practicing. This is a difference squares. This is one you should recognize. Comes up a lot in algebra classes. So you square root both, and the one will be plus, and one will be minus. And then that one doesn't factor, so you got to leave it alone. Now you're going to set each of these factors equal to 0. Okay, once you set each factor equals 0, you're solving them individually. And remember the shortcut. If I want to get x by itself, I move the 3, change the sign. So that's negative 3. Move the 3, change the sign. So that becomes positive 3. This one, I subtract 5, and then I square root it. So we get two imaginary solutions, which won't give us, you need the real numbers to get x-intercepts. So our x-intercepts, so basically we throw that away for x-intercepts. Okay, so those are imaginary zeros. So our x-intercepts are negative 3, 0, and 3, 0. Okay, now let's go to Desmos. Okay, so I got it in Desmos, and this is actually a good example of why you want to be able to do some of this by hand. Because if I just look at this screen and I have no idea what this graph is supposed to look like, I can miss things. So you can see my x-intercepts, and I already know that that's all of them. But if I zoom out, right, then I can kind of see the shape. And again, we would need calculus to figure out what these turning points are. We can kind of estimate it. And then our y-intercept is 0, negative 45. So that jives with what we figured out algebraically. And it's x to the fourth. So you should notice that the left end and the right end are both going up, right? Even power, positive leading coefficient. So the left end and the right end are going up. We did our algebra to figure out what the x-intercepts were, negative 3, 0, 3, 0. We did our algebra to find the y-intercept. And then if you go on to calculus, you'll learn to find these turning points. Without calculus, you just have to plug in some points and try to estimate where that is. Or, you know, you basically plug in a bunch of values and try to figure it out. Comparing smooth and continuous graphs. The degree of a polynomial function helps us to determine the number of x-intercepts and the number of turning points. I was alluding to that earlier. A polynomial function of nth degree is the product of n factors. So have at most n roots or zeros, or x-intercepts, right? So if it's degree 5, you can have up to 5 x-intercepts. The graph of a polynomial function degree n must have at most n minus 1 turning points. So if it's degree 5, 5 minus 1 would be 4. You can have 4 turning points, 4 humps, 4 peaks or valleys, the way I kind of think of it. Okay? This means the graph has at most 1 fewer turning point than the degree of the polynomial, or 1 fewer than the number of factors. A continuous function has no breaks in its graph. The graph can be drawn without lifting the pen from the paper. A smooth curve is a graph that has no sharp corners. So like the absolute value, that would not be a smooth curve because you have that sharp corner. But a parabola, right, when you hit that turning point, it's smooth. So that's the difference there. The turning point of a smooth graph must always occur at rounded curves. The graph of a polynomial functions are both continuous and smooth. Okay, so that's a characteristic. If it's a polynomial function, you're going to get a continuous graph, meaning you can draw it without any breaks. Everything's going to be defined. You know, your domain will be all real numbers. And when you draw it, you can draw it without picking up your pencil. So if it's a x to the third, it might look something like that with two humps. And it could have up to 3, depending on where the x-intercept. It can have 1. If I touch it right here, it would have 2. If I touch it right here, it would be 3. So it can have up to 3 x-intercepts. Right? If my x-axis is here, it only have 1. Okay? So let me erase that last line. Example 10. Determine the number of intercepts and turning points of a polynomial. Without graphing the function, determine the local behavior of the function by finding the maximum number of x-intercepts and the turning points for f of x equals negative 3x to the 10 plus 4x7 minus 4x to the fourth plus 2x to the third. And again, what's going to determine is the degree. This is degree 10, so the highest degree. So you can have, so that tells us up to 10 x-intercepts. And then you subtract 1, and up to 10 minus 1 would be 9 turning points. And you don't have to graph anything. So we can expect up to 10 x-intercepts and up to 9 turning points. Okay, so example 11, drawing conclusions about a polynomial function from the graph. So what can we conclude about the polynomial represented by the graph in figure 12 based on intercepts and turning points? So we have 2 x-intercepts. So that means it has to be degree 2 or higher, right? But if both ends are going up, you should also know that it needs to be even. You can also say that if you want, but they're just saying based on x-intercepts. So based on x-intercepts has to be 2 or higher, but then the turning points, you got 1, 2, 3 turning points. So remember, turning points is going to be 1 less than the degree. So that means the degree has to be degree 4 or higher, right? Because we're going the other way. So if it's degree 4, it can have up to 3 turning points. So it has to be degree 4 or higher, and technically higher by even degree. So it has to be 4, 6, 8. Okay. All right. Example 12, drawing conclusions about polynomial function from the factors. So given f of x equals negative 4x times the quantity x plus 3 times quantity x minus 4. So you can see we have 3 factors with x in it. So if we set this equal to 0, oops. All right, let me restate that. So determine the local behavior. So we're going to basically put all that together. We're going to find the x-intercepts, the y-intercept. So let's start with the y-intercept. So we're putting in 0, f of 0. Okay, so if we put in f of 0, we get, well, negative 4 times 0 is 0, times 3 is still 0, times negative 4 is 0. So that 0 makes the whole thing 0. Okay, so our x or y-intercept is 0, 0, which also will be one of the x-intercepts. So again, the x-intercepts, you have to set it equal to 0 and factor it. So it's already factored for us, so that makes that part easy. So we got negative 4x equals 0, x plus 3 equals 0, x minus 4 equals 0. So x is 0, x is negative 3. Remember the shortcut, we just move it, change the sign. So our 3x intercepts are 0, 0, negative 3, 0, and 4, 0. And then, based on that, having 3x intercepts means that we can have, this has to be degree 3 or higher, and at most, if it's degree 3, so it's degree 3 or higher. Well, if we multiply it out, you can see it is degree 3 exactly. But based on the x-intercepts, you have 3 x-intercepts, so it has to be degree 3 or higher, and it can have at most 3 minus 1 is 2 turning points. And then if we want to go further, if we multiply it out and figure out what the leading term is, I think you'll get like 4x to the negative 4x to the third. So if you even want to go a step further, it's going to look something like this, possibly, right? Because you can have 2 turning points, 3 x-intercepts, and then since it's negative x to the third, the left end goes up, the right end goes down. Okay, that was extra. That was bonus. This is all the you wanted the y-intercept. So the question just wanted you to figure out the y-intercepts, x-intercepts, and discuss based on that what the degree is and how many turning points. And that brings us to the end of the lesson. So again, I want you to practice, practice, practice. Make sure you go to the end of the section in the book and do all the exercise, all the odd exercises at least, right? And or as many as you can. And then if fill up to it, do a few of the even ones as well. All right, have a good day and see you next time.